All kinds of strange, wonderful craziness occurs in quantum theory. We're going to finish out quantum theory today, okay? And then hopefully we'll get into nuclear stuff so that we are ready for our test on Friday. We probably won't make Friday, but we'll see. Okay, let's say that we've got a surface here, and this surface is insensitive to wavelengths that are less than, let's see, what should we do? 544 nanometers. So this surface is insensitive to any wavelength. I shouldn't say less than. I should say greater than. Anything greater than that, no photoelectrons pop off, okay? So, here's my question. What's the work function of this? Number one. Question number one, what's the work function? Question number two is if you hit this thing with violet light. Do I have violet? Oh, I think I'm out. We'll use blue then. If you hit it with blue light of wavelength equals, let's say, 650 nanometers. Okay? No, that won't be right. 450 nanometers. I'm getting my stuff backwards.
Insensitive to wavelengths greater than that, right?
Yes. So
Okay,
this
so-
at this you get
No.
at this here at wavelengths less than or equal to that you get electrons. Does that sound better?
Yeah.
Okay. At wavelengths of that and less, you get photoelectrons, okay? So I want you to tell me what's the work function for this material, and the second thing is if you hit it with blue light, okay, what will be the max kinetic energy of ejected photons? And then number three, what voltage difference will be required to stop these photons, not photons, electrons. Man, I'm messing up today. Electrons. In a photoelectric circuit. Okay? Okay, find those three things. We're talking about these photoelectrons from part B when you're trying to stop them in part C. Thank you. That's an excellent question. Yes, that's electrons. Sorry.
Well, it doesn't matter.
So are there no electrons being ejected?
So, sorry. Photons are coming down. I'm getting my photons and electrons mixed up when I'm writing on the board. This is a photon, and the electron is ejected, okay, with kinetic energy. All right? So that's electron being ejected in part B. That was my mistake. Sorry. I said photons. Let me talk about part C. All right. Sounds like we're making good progress. Let's go through it, okay? Okay, here we are. Here's the key. The key right here is this statement. And you're looking for this statement because if they give you this statement, this means that this is your threshold wavelength, right? Threshold wavelength is 544 nanometers. That means any wave with less energy than that one won't be enough, right? Won't be enough to break it free from the from the amount of energy that the atoms are holding onto their electrons, right? So it's not going to be any bigger than the work function. So the deal is that, remember, our electrons are buried in this energy well. And this energy well is the work function deep, right? And so our photon comes in. Actually, I shouldn't draw a real wave. I should draw a little wave packet, right? My little photon comes down here, and it has energy of HF. If the HF of this thing is not bigger than that, it can't break it free, right? So when you're at the threshold, it breaks it free, but when it breaks it free, what's the kinetic energy of it? Zero. That's the key. The maximum kinetic energy is zero because you have just enough energy to break it free, but it doesn't have any energy left over to go anywhere and do anything. So it just breaks free and floats there and probably falls back in. Okay? All right, so that means Kmax equals HF minus work function. At the threshold, that's zero. Now remember our little trick. Remember that this right here, frequency, C equals frequency times wavelength, right? Because it's a wave, behaves like a wave. So frequency equals C over wavelength. And I can substitute this in since I've given wavelength, right? So this becomes 0 equals hc over lambda minus the work function. Actually, I'm just going to move the work function over here. Is that okay?
Yeah.
So I move it to the other side. And so when you're at the threshold, this will be true. The amount of energy of the photon equals the work function. So my question is which HC do you use? You know, whichever one you would like to in this case, because this is 544 nanometers. I could use the 1240 EV nanometer one, because then my nanometers will cancel directly, right? That would be the easiest one to use. And then I'm left with, what, 2.28 EVs for my work function, right? Could I have used the other one, the HC that has joules in it? I sure could. I could have used 1.99 e to the negative 25th joule meters over 544, but then I got to put e to the negative 9th meters, and I could have figured this out in joules if I wanted to. Did anybody do that?
Me.
You did?
Colin
What'd you get, Colin?
3.6 e to negative 19 joules.
Okay. Okay. Which answer is correct? The answer is both of them are. Okay, as long as you put your units on. Okay? All right, now it says we've got blue light. So now that we got blue light, we have a new wavelength. All right? So our equation, Kmax equals HF minus work function, or HC over lambda minus work function, Kmax. And it's probably going to be easier for us if we work it in EVs this time. Because, well, I guess it doesn't matter. If you use this in joules, you just plug that in for joules here, and then you plug this one with joules, and you still get the same answer. Your energy is just going to be in joules. Okay? So I use the 1240 EV nanometers here, divided by 450 nanometers, minus my work function in EVs, because I'm going to have EVs here. So I get 2.28 EVs, and I end up with 0.48 EVs. Done. Okay? That's my max energy. Or, Colin, what'd you get in joules?
7.64 e negative 20.
Okay? 7.64 e to the negative 20 joules. Either one. All right? Fair enough. Now, the last question sounds a little tricky. Turns out to be really simple. What's the delta V? That's the delta voltage that's required to stop the electrons in the photocircuit. Okay, remember, your photon energy comes down. You have the work function to break, and then this thing leaves with kinetic energy. And remember, the way they measure that kinetic energy is by putting a battery in here that charges this up negative and makes this positive, which makes the electron want to turn around, stop, and come back. Okay? So the question is, if this thing has kinetic energy of 0.48 EVs of energy, kinetic, when it comes over here and stops, what kind of energy will it have?
Potential.
Electric potential, and the electric potential equals the kinetic energy max. That's 0.48 EVs, but electric potential energy, we find that with V times Q, right? And my Q is
1 electron.
1 electron. It's an E, right? And look at this. So how many volts do I need? 0.48 volts.
Do we have to like show that on the?
No, you don't really.
So you can just say.
So the reason I wanted to show you this is because sometimes you get this graph, kinetic energy max versus frequency. And remember, our graph looks like this, where this is the Planck's constant, and then down here, that's our work function. Remember, we don't graph this bottom part because it doesn't really exist. There's no negative kinetic energy. But where it would cross is the work function, right? And remember, for different materials, it just shifts right or left or up or down, depending on how you want to look at it. Okay, material 1 and material 2. But Planck's constant is always the same, right? Okay, they could, on this graph, not put kinetic energy here. They could list instead what was the stopping potential. How much voltage did it take? The stopping voltage to stop the electron. Because that's what they really dial up on this battery here. So, how do we turn that into kinetic energy?
Slap on an electron.
Slap on an electron is exactly right. So if this reads 1, 2, 3, 4 volts, then if we multiply that by the electron that will be flying across, then it magically turns into kinetic energy, and this turns into EVs, right? And that's all the change you need to make. I just wanted to emphasize that you know what the Q is. The Q is 1E, so you can turn the volts into EVs just like that. Okay? Does that make sense? Because that shows up occasionally, and students sometimes see stopping potential and they freeze, and I don't know what to do with that, and they quit when it's not a big deal, right? Okay, so there you go, a solar cell, right? Solar cell. So what we do in the real world is we do not put this backwards voltage on here. What we do instead is we put whatever device we want to run right there. Shine light on it. The electron flies across, collects, goes through here with current, and makes our device run. Okay? That's our solar cell. All right, so there you go. Photoelectric effect. Now, let's do the opposite of the photoelectric effect. All right, here we go. What if we did this instead? What if we built a capacitor plate that looked like this? Okay? So that this side was all negative, and this was my positive side. Actually, you know what? I'll tilt it the other way. I'll leave it like that. That's all right. What? The way it's tilted? Actually, I'll tilt it the other way because I want to do something with it. All right? So I'm going to tilt it this way. No, it really doesn't for my picture. All right, so if I dial this voltage up to really big, a really big delta V, then what will happen is, because I got a pointy spot over here, the charge will start to jump off. I get it high enough that it'll start to stream across. And electrons will jump off of here and fly over here and hit this piece of metal. And they'll be absorbed by the metal. And when they're absorbed by the metal, what happens to their energy? Some of it will be absorbed. The piece of metal might get a little warmer. But what happens is the electrons will fall into the atomic structure. And when they do, it'll emit, the electron will get, the electron will get trapped, and it'll eject a photon. Now, guess what?
The reverse.
What kind of energy? Yeah, it's like the exact reverse of the photoelectric effect. So instead of a photon hitting here and an electron flying across, you've got an electron hitting a piece of metal and knocking a photon off. Okay, so what kind of energy does this thing have right here?
Oh, electric.
What do you mean?
Electric potential to start. When it flies across, it turns into
Kinetic.
kinetic. And then after kinetic, it turns into
Like,
light. What kind of energy is that?
Electromagnetic.
HF, right? Okay, at best, conservation of energy dictates. How much energy can that be? Or what's the upper limit of what that can be?
Electric potential minus.
Whatever I started with there, right?
Isn't it minus the, or you add on the...
Now there is a lot of physics involved in how it drops in, what is the likely X-ray and all that. We're going to keep it nice and simple. So at the upper limit, roughly speaking, the upper limit that we would get would be this V cubed, right, would turn into HF. And if all of this turns into this, then you would get a maximum frequency, right? And you could figure out what the maximum frequency would be, roughly speaking, right?
Not a frequency?
What's that? Okay. So what if this is 10,000 volts? If that's 10,000 volts, how much energy do I start with?
10,000 electron volts.
Very good. 10,000 EVs, and that's going to turn into HF maximum that I would get. And which H would I use?
The electron volts.
Yeah, say the one with EVs in it, right? Now, not the HC, but just the Planck's constant, right? So that's going to be the one that is
4.1.
4.14 e to the negative 15 EV.
Seconds.
Oh, EV seconds. Thank you. Okay. So what we're going to get is that's 1, 2, 3, 4. 1, 2, 3, 4 divided. No, it's going to divide this way. So we're going to get, yeah, 10,000 divided by that. So your max frequency is going to be whatever that number is. What does that turn out to be?
The big number.
Yeah, you were too fast with the calculator.
2.42 exponent to the 8.
2.4 e to the what?
18.
18
Now we're not.
Yeah.
hertz. Hey, does anybody have an idea? Is that visible light?
I think it's positive.
Yeah, it's positive.
Yeah, positive.
Oh, there we go. Positive 18. There we go. Visible light is somewhere in around the 10 to the 14th hertz. Okay? We could figure out the wavelength of this if we wanted to. We're going to find out it's much smaller than visible light. Way smaller than 400 nanometers. Okay? This turns out to be an X-ray. And this is how, when you go to the dentist or you break a bone or you got Dane Bramage, they put you right
Oh,
there.
get it?
And then they put a piece of film behind you. And they take a picture of your insides. You finally got it? All right. And that's what they do. Essentially, it's a very high voltage capacitor where they shoot the electrons across. It hits here, and then they have like a. This is kind of in a. They got a little window here where the X-rays can come out. Okay. And they make that come around like that, so they're trapped inside. So they don't shoot everywhere. Okay.
I remember when I was
And that's it.
and I broke my arm, and they told me like, put it this way and that way. I was like, why are you leaving the room every time you take an X-ray?
Exactly.
I'm scared.
Yeah, this must not be good.
I know.
Actually, it's not good for you if you get lots of it. Now, your body is designed so that if you get X-rays and you get a little DNA mutation, no big deal. Your body fixes most of those things, right? It's only when you get just that one special one that your body can't deal with very well, or when you get lots and lots of them that your body can't keep up with damage control, like when you have too many x-rays over the course of a period of time. So like for instance, you don't get dental x-rays. Some of you go to the dentist and you get dental x-rays, right? They don't do it every time you go. They usually do it once a year, okay? And the person that takes your x-rays always leaves the room. One of the things they discovered is that it came out of Einstein's relativity ideas, was he came up with this crazy thing, E equals mc squared, okay? Mass energy equivalence. So Einstein was the first one that I know of anyway that put forth the idea that we need to expand our idea of energy and we need to expand our idea of mass. That mass is technically a form of energy. Okay? Well, it's like coagulated energy, right? In the form of mass. And he said that mass has energy in it. And this is how much. Okay, so everybody real quick. Take your weight. Okay? Take your weight in pounds. We need to convert that to kilograms. So if we divide that by 2.2, that will give you your weight in kilograms, or your mass in kilograms, all right? That equals your mass in kilograms, okay? Now, take that mass in kilograms, plug it up in here, and then plug in c squared, which is 3e8 meters per second, square it. And then give me just the order of magnitude of your energy.
18.
18.
E to the 18th joules, right? E to the 18th joules. Okay, that's what? Yeah, that's a billion times a billion joules of energy. That's right. Now, let's just figure it out. How long could you run a 100-watt light bulb? Okay?
Are you E19?
You'd burn the light bulb.
So, you are times 10 to the 18th joules, or 10 to the 18th joules.
Yeah, 5.9.
All right? And that's power times time. So that's 100 watts times time. So how long could you run a 100-watt light bulb if we converted you to energy?
10 to the 16th second.
10 to the 16th seconds. All right.
That's useless.
How many seconds in an hour?
2,600.
3,600 seconds in an hour. 1 hour, 24, oh, that's day. 24 hours. Still screwed up.
Yeah.
24 hours equals 1 day, and 365 days equals 1 year. So how many years could you run that light bulb?
18 to the, like, to the,
To a lot of decimal places.
9.
So, 10 to the 9th years. That's a billion years.
We're doing great.
Or,
On one.
one person. Or that means that we could take you, if we could convert you all to energy, that you could run a billion light bulbs for a year. Now, that's a lot of energy encased in mass. Right? Okay. Now, we've got to rethink this thing then. Since energy and mass are two aspects of the same thing. You remember in chemistry? Shh, be very quiet so the chemistry people next door don't hear. You remember chemistry last year and the year before when they talked to you about conservation of mass and chemical reactions? If you have two chemicals that combine and in the reaction they give off heat, where does the heat come from?
Mass.
It comes from mass. If you have a chemical reaction, it absorbs heat. Where'd the heat go?
Mass.
Into mass. Now, in a chemical reaction, the amount of energy that is released or absorbed is so small compared to this c squared that we ignore it in a chemical reaction. It's there, but it's tiny. Okay, it's very tiny. Now, in a nuclear reaction, that is not the case. In a nuclear reaction, when like in nuclear fission, where an atom is broken into two pieces, okay, the mass of the parts afterwards is different than the mass we start with. And the difference in the mass is because of the energy either released or absorbed in the process. Does that make sense? So what we're going to do now is we're going to change what we consider conservation of energy and what we consider conservation of mass. In reality, it's conservation of mass energy. So what you have to do is this. So like in a nuclear reaction, if we had an atom that cracked into two pieces, and afterwards, these two pieces flew off. And when they fly off, they flew off with kinetic energy. I'm doing this and I'm violating conservation of momentum here.
We're morally depraved.
All right, so they fly off this way. So I don't violate conservation of momentum. All right, and they've got kinetic energy now. And there might have been like gamma rays released. HF, gamma rays. Okay? Okay, here's the deal. The mass energy we start with has to equal the mass energy we end with. Okay? So normally we do this in terms of energy, and not in terms of joules instead of kilograms. So what we would say is, how much mass did we have to start with? Well, the mass of my original object times c squared. That's how much energy I began with. How much energy do I end with? Well, I end with an mc squared energy for this part, plus an mc squared energy for the other half, plus the kinetic energy they have, plus the energy of my photons. Does that make sense? So, mass energy before equals mass energy plus kinetic energy plus photon energy. It's all just conservation of energy, just like we had before, except now our energy, we have a new term, mc squared. All right? So do you see that these two have to have less mass than we started with? Because some of their mass has been converted into this stuff. Okay? So, E equals mc squared. Kind of crazy, but it turns out to be true. Turns out to be absolutely true. Now, watch this. E equals mc squared. I'm going to rewrite that. E equals mc times c. Now you know what mc is?
Yeah.
No, not MC Hammer. You're going way back.
Ian's fault.
Ian's fault. Ian listened to MC Hammer?
Curtis Club.
Let me rewrite this. What's C?
Speed of light.
Speed of light. So really what that is
Mass
that's
volume.
mv
Momentum.
times v. What's that?
Momentum.
Ah, so what this is momentum times c. The momentum of a
Particle or whatever.
something moving at the speed of light, right? No, stop it. All right, so here we go. Energy equals mc squared, but it also equals pc. Momentum times the speed of light. But wait, there's more.
There's more.
Yes.
But doesn't E equal HF? Yes.
Apparently.
And because C equals frequency times wavelength, that is HC over lambda, right? Oh, come on, it's not that hard.
This means all energy is light.
That's equaling too much stuff.
Okay, so all of this means that E equals E, or PC equals HC over lambda,
Yeah.
right? The C disappears, and I'm left with that momentum equals H over lambda.
That was crazy.
All right,
Light has momentum.
right. If we're talking about this for an object that will travel at the speed of light, right? Then objects that travel at the speed of light will have this momentum, and because they're waves traveling at the speed of light, you can calculate the momentum of a photon. Now it seems really weird. A photon is a massless blob of wave energy. Massless. It has no mass. So if it has no mass, how can it have momentum? And the answer is because energy, anything with energy, has properties of mass. And so objects with mass have energy. Objects with energy have the properties of mass. And so they can have momentum as well. That means that if you're standing there, I can throw a bowling ball at you and knock you over. Or if you're standing there, I can throw a photon at you, get out a flashlight, shine it on you, and in theory, I can knock you over. Poke a hole in him. So we shine a photon on you, it hits you and bounces off you, and then you should recoil, right?
Like insignificant.
Yeah, the deal is that photons have such small momentum that we wouldn't notice this in general. In fact, to knock you over with light, the light would have to be so bright, so many photons, to knock you over that you'd probably catch fire, so it wouldn't be any fun. Okay? So, yeah, that's because you have too much mass, right, for this to really be effective. However, what if the object is really tiny? Like, say, an electron, and I shoot a photon at it. And the photon hits the electron, and the photon bounces off. And let's say the photon comes in like this, and the photon ricochets off like that. What's that thing going to do? Think pool. Think two-dimensional momentum.
Go to the other
It's going to go which way?
at that other angle.
It's going to have to go this way afterwards, right? Because the momentum we have to start with is this way. And therefore, the momentum I end with, must be the same. So the momentum up of this photon and the momentum down of this electron must be the same, and the x momentums must add up to be my original. Whoa, it's a two-dimensional collision with photons and electrons.
Well,
This is called the Compton effect.
Wait,
Why is that funny? Because of Compton?
What is
Out in LA area?
the South Central.
The South Central effect.
What's the
That's where the
Compton
MCs come
effect?
from.
The Compton effect is this.
Yes, I like it. Is that a word?
The Compton effect is essentially, it is
Where'd it go? See?
Compton effect is the momentum collision between photons and electrons, usually. Could be protons, but it's just, when they start getting bigger, the effect gets smaller and smaller and smaller. Now, watch this, listen. If this one starts off with momentum, what's the momentum of this photon?
H over lambda.
H over lambda. And it has this momentum to start. When it hits this electron, it gives the electron momentum and energy. What happens to the momentum and energy of my photon then?
Goes down.
It must go down because now this electron has mv, momentum it didn't have before. Which means that the momentum of my electron has gone down. Wait a minute. If the momentum of my electron has gone down, what's happened to it? H over lambda. If that goes down,
The wavelength increased.
wavelength goes up. And my photon just changed color. Ooh, there we go. All right? My photon changed frequency. So if we could see it, that would mean it would change color. Now, if it started off as blue and hit this and knocked it, and then its wavelength would decrease, no, its wavelength would increase. So it would move from blue towards green. Okay? It's pretty neat, actually. There you go. This is called the Compton effect. Now, there's an equation that goes along with this that tells what the change in wavelength is, but if they need it on the test, they'll have to give it to you. But there will be, there's an old one, I think, in fact, it's in your review packet. Look in your review packet. If you get out your review packet,
Part that remains.
the part that remains. Okay, the page right after the one you ripped out, flip it over and you see this. See this page right here? Look on the bottom. Actually, we just covered this whole page. On the top, that's X-ray production because an electron is hitting an anode producing X-rays. That's X-ray production, the opposite of the photoelectric effect. All right, on the bottom, this is the exact same picture I drew. Photon hits an electron, the electron takes off, the photon scatters, and they want to know what's the new energy of the electron, or what's the energy of the electron, what's the magnitude of the momentum of the recoiled electron. This is a hard problem, this Compton effect here, because it's two-dimensional. Okay, on the test, they're likely to give you, it would probably be a one-dimensional collision. And it would be like this then.
Just move straight forward.
Your photon would come in, hit your electron.
Slow down.
This is at rest, and you can have two things happen. H over lambda is your momentum here, and your momentum here is 0 to start. You have two options. Well, actually, you really only have one option. Because the photon can't move slower than the speed of light, right?
Yeah.
So it can't hit the electron, knock the electron forward, and then go through the electron, right? So it's got to bounce back. So what happens is it'll hit and recoil and turn around this way. Now be careful. If to the right is positive, that means the new momentum is a negative, right? And so the change in momentum here would be the momentum mv that this would have, right? Does that make sense? It's exactly like a car hitting another car, where this one's at rest, this one hits and recoils, right? It's the exact same problem, except instead of the momentum being mv and mv, it's h over lambda and nothing here. And then afterwards, it's a negative h over lambda equals this. So it's going to be like this. Momentum before equals momentum afterwards. Okay? And so I get h lambda before equals negative h lambda plus mv for my electron. Now be careful. This is going to be wavelength 1, and that's going to be wavelength 2. They won't be the same wavelength. Okay? So it's just momentum, but now we got a photon to deal with. Okay? So that one very likely could show up. Or they could ask you a question like this. A photon hits and scatters off of an electron, giving the electron some momentum or something, or the electron takes off. Then they'll say, what property of the photon has gone up? They say, well, has the frequency gone up? Has the wavelength gone up? Has the energy gone up? Has the momentum gone up? Okay, well, energy for a photon is hf. So, and momentum for a photon is h over lambda. So when it goes through this collision, it's going to lose momentum, it's going to lose energy, so therefore it's going to lose frequency, but it's going to gain wavelength. Does that make sense? That would be a multiple choice question they could ask. Something like that about this effect. What's that? Free points? That's right, it's free points, it's so easy.
Yeah.
Okay, that's called the Compton effect. So, on your equation sheet, when you get your equation sheet out, look for the equations you have, and so far, let's see if anything's been left out of what we need. We've got E equals HF, so this is for a E and M wave. And then they give you PC, so we're good there, right? They give you photoelectric effect, K max equals HF minus work function. You've got wavelength equals H over P. Oh, that looks different.
Didn't we do that a little while ago?
Didn't we just do that a little while ago? Yeah, but I wrote it this way, right? It's just flipped around, right? So it looks a little different. Okay? And then you've got delta E equals delta MC squared. And they're just saying the change in energy is equal to how much mass changes, right? In a reaction. Okay, now that's all the equations they give you. Dun, dun, dun. Yes. All right, so there we go. Got all this stuff? We okay? So we've covered photoelectric effect, X-ray production, mass energy equivalence, and momentum collisions with photons called the Compton effect. Where were we? Oh, a graduate student in, I think he's in France, by the name of yeah, it looks like de Broglie or de Broglie, but it's French, so of course it's not pronounced like it's spelled. De Broglie. No, I think it's pronounced de Broglie. De Broglie, graduate student, he says, what the heck? He says, look, photons now have properties of mass. Photons have momentum. They got energy. They're acting like particles. HF, you got the photoelectric effect. He says, I wonder, since waves, these things we thought were massless, now are acting like particles, I wonder if particles could behave like waves. And so he goes through his whole dissertation and all that, and he comes up with his paper, and he submits it to his professors. And he says, look, yeah, the professors were in a big quandary, because he said, look, the wavelength, we just said that P equals H over lambda for a wave, but he said, hey, the wavelength of a particle is just equal to H over P. But P for a particle is MV. So this equation works for both waves and particles. But if it's a particle, then you can shove in MV for the particle. And he argues it through, and the professors get it, and they're in a bad way. Because look, they said, it looks reasonable. It looks very nice. But if we accept his paper and say that we give it a stamp of approval and graduate this guy with his graduate degree, and it turns out to be wrong, we look like idiots. So we can't pass it. And then they said, but wait, what if we don't pass it and somebody else comes up with the idea later and it's correct? Then we'll look like idiots. So what do? So they sat on the paper supposedly for quite a while, several months, and they're like, we don't know what to do because we have no way to test it. There's no way for us to know whether it's correct or not because there's no experiment that we can think of that can prove it.
I think they look like idiots by not being able to decide. So
Yeah,
I
well,
really didn't look like it.
So they're arguing about it, and finally they said, well, let's send it to a higher authority. So they sent the paper to Einstein. And they said, what do you think? And he goes, I think it'll work. And so, cha-ching, he gets approved. He gets the stamp of approval. Now remember, what is the experiment that shows that photons are particles? Photoelectric effect, right? Photoelectric effect shows that waves behave like particles. What is the experiment that shows that photons are waves?
Double slit.
Double slit. Very good. Young's double slit experiment. Ooh, that's ugly.
That was ugly.
Quiet you. When you send waves through here, if you send particles through here, they should just go through right there and cause a pattern that looks like this, right? But what we find for waves is when we send the waves through here, what we actually get is much more interesting, and it looks like this, right? And there's no way to account for that if it's a particle. So this experiment proves that light is a wave, this experiment proves that light is a particle, and then we come up with wave-particle duality. So, eventually somebody comes along and says, hey, why don't we just shoot electrons through something like this and see what we get? All right? And here's what they got. Here's the screen. Now back then, this is what they did, is they shot electrons through there and they had a fluorescent screen, and you could just see where they hit. Makes a little glow. And so one would hit here, and then one would hit here, and then another one would hit here, and one would hit here, and one would hit way up here, and then one would hit here, and then another couple here and here, and then one here, and then one here and here and here and here, and it ends up looking like this.
A particle has a wavelength of a Hawk.
What is that?
A wave.
Diffract.
That's an interference pattern. Crazy. Now that's not the spookiest part. They eventually get so good at this experiment that they can shoot a single electron through at a time. Alright? And when they shoot a single electron through at a time, guess what they get? It only hits ever here, 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 or here.
So it's only whenever they're more that repel each other.
And never hits here, or here, or here, here, here. So what they have real trouble with this understanding, and it's real very spooky still today, even though we've seen it now for 100 years, is that a single electron, as it passes through here, interferes with itself and forms an interference pattern. That's really weird. Okay? Now, it just is. We understand that that's the way it behaves, even though to our normal, everyday world, that's spooky. But in the atomic world, that's normal.
That's normal.
It's weird. It's really strange. So like, if we lived in the atomic world, you would be a particle that had a wavelength, and we wouldn't know exactly where you were.
Here? You're right here.
That's right. The Heisenberg uncertainty thing is because of this, that you have a wavelength, and where you're at, it's a probability of where you'll be located. You're most likely going to be here, but the next time we open our eyes, you might be over here. Yeah. In the strobe light, you're all over the place. This is an electron microscope. Yeah, you do. You have a little object down here, and you want to see what it's like. And so you shoot electrons at it. Why do we shoot electrons at it? Why don't we just shoot light at it? Okay, because the deal is that electrons, you can control their momentum. They have a certain mass, and there is a certain Planck's constant, always, right? You can control their velocity by what potential difference you accelerate them through, thereby changing their wavelength, and you can make their wavelength really small. And then when they hit the object and bounce off, they form an interference pattern, which for all of us that take photographic pictures, that's called a picture, because an interference pattern forms on a piece of film, giving you a picture. That make sense?
No.
No. All right? So we can have really, really small wavelength for the electron. Okay?
Okay, I get that.
They've got proton imaging now too. So they have a proton microscope. And you can get even smaller wavelengths because the mass is larger, therefore making the wavelength even smaller. So you can do proton imaging. Okay? All right. So de Broglie wavelength. Okay, so here you go, everybody.
Yeah.
What kind of problem will you see this on?
The bad.
What?
Okay, here you go. Look at this.
Okay.
An electron flies across here. When it hits this plate, how fast is it going?
100,000.
Don't say the speed of light. No. How would you find it?
Get kinetic energy.
Okay, you go from electric potential to kinetic, so that's QV equals 1/2 mv squared. Now, if I'm going to do that, remember, what kind of energy unit do I want?
Joules.
I want joules because I'm going to find velocity, right?
Okay.
Okay, once you find the velocity of the electron when it hits here, they can say, oh yeah, by the way, what's the de Broglie wavelength of the electron right there?
All of the types of
Smallest.
It's what? H over P, which is H over momentum. So whatever velocity you get here, plug it in there, put in the mass of your electron, put in the appropriate Planck's constant, and you get the wavelength. Okay? So they're going to throw this, find the de Broglie or de Broglie wavelength in all kinds of different problems. They're going to have an electron flying through the air, and they're going to say, oh, what's its de Broglie wavelength? Just calculate it. Okay? It's not a big deal. All right? Now,
Just for about what percentage of the
I've
AP
been waiting on
exam
the
is
pen.
modern physics?
I've been waiting on this pen.
modern physics is 10% of the exam. Okay, let's backtrack a little bit. They discovered what the atom was like. Remember they discovered with the Geiger-Marsden experiment, they discovered the Rutherford model of the atom, which is that the nucleus is about 10 to the negative 14th meters across. And the atom itself is 10 to the negative 10th, about an angstrom across. And the big question was then, okay, if that's the atom, then what the heck are these things doing out here? And the obvious model was that they would go in orbit. Okay? So you would have these things going around. The problem with that is remember that when you're going in a circle, you're accelerating. And accelerating charges radiate energy. And when they radiate energy,
They lose energy.
they lose energy and they'll decay. And so within like a billionth of a second, these things would decay down, and so your atoms would disintegrate. So we know that the orbital model is not correct. And along comes Niels Bohr. And Niels Bohr says, here's how the hydrogen works. You got a proton here, and you got electrons going around like this.
The atom or the hydrogen?
That's a hydrogen atom, what's it?
Oh, yeah. He says, look, that electron can exist here or here or here. Okay? If you want to move from here to here, you need to add energy. Energy in. Yes. So this is the ground state from chemistry, right? This is the first excited. This is the second excited. Right? And he says you got to add energy to get up here. Okay? Where does that energy come from? He says, well, you get this energy from a photon. A photon comes in, HF, it has to be exactly that energy, and you jump from here to here. If it's exactly this energy, you jump from here to here. What if it's in between? He says it won't work. Okay?
How's it in there?
He made it up. Because people said, but this won't work. orbital stuff we know won't work. And he says, well, yeah, of course. In between here it won't work. They'll decay, and they'll fall from here to here. And when they fall back down, when they fall this way, what happens? They radiate energy, they lose energy in the form of a photon of HF. And they said, yeah, okay, but wait. What about these places? He goes, well, they're special places where it won't radiate energy. There will be special spots where it won't radiate energy, and everywhere else it'll radiate energy as it falls down, and it'll absorb energy to move up. And they say, why not? He says, because they don't.
That's right.
That's the excuse. There's special areas, there's special.
And he was exactly right.
Ooh.
Now we understand now why there's these special spots. Why do we have special spots? Okay, remember that electrons now have a wavelength. Okay, let's go way back. Do you remember a string? You remember a string with a wave in it? Do you remember that you can send certain wavelengths through here and it will resonate and you'll have resonance in a standing wave, right? But if you send in the wrong frequency, it won't do anything, right? It won't exist. Guess what? If you figure out the wavelength of an electron in a hydrogen atom, guess how long that is? That's the first harmonic spot, where it'll set up a standing wave with itself. So you get a constructive interference here, and you get the second harmonic here. You get constructive interference here. You get the third harmonic here, constructive interference here. So why can't they exist here? Because you get destructive interference, because this is like a wave and a half, or like 3/4 of a wave or something, where you don't get constructive interference. So, you remember in chemistry, S, P, D, F, all the different shells, the electron clouds? The reason they're there is because that is where they have constructive interference with themselves. That's why they exist in that region, but not other regions. Okay? The electron physically can't exist here because it has destructive interference with itself, so it won't show up there. But it's okay for it to be here and here, and here. Does that make sense? Because they're behaving like waves, that's the way the electrons show up in the shells. All right? Where they have constructive interference. All right. So, what do we care about all this? All right. This, hopefully, is all review from chemistry. Chemistry, remember you have the ground state, first excited, second, third excited, so forth, so on, right?
Yes.
And eventually you get out to this spot out here where they're free. And that's n equals infinity. Anything above that is where it'll be ionized. Okay? Yes?
From N to 3 to N4, is that supposed to be larger?
I'm making up a theoretical one. Okay? Now, in the real world, the ones down low generally have a bigger jump. But, okay, they could make any kind of atom they want on the exam. Right? So, you're used to seeing ones that look like this, where they get closer and closer as you get farther out. Could they give you one on the test that looks like this? They sure could. Okay, so don't let the levels mess you up. Whatever they give you, just work with it. Okay, there are two numbering systems. The numbering system where this starts at 0, first, second, third, excited. And then there's the quantum number one where it's N1, 2, 3, 4. So be careful about which one they give you. Okay, don't get them confused. The electron starts down here, and I'm going to give you some numbers. Let's call this negative 13 EVs. Call this negative 8 EVs. Call this negative 6 EVs. Negative 2 EVs. Actually, make that negative 1. And then make this 0 EVs up here, because once you get up to 0, they're free. All right? Now, the reason why they usually put a negative numbering system is because negative means trapped or bound. Okay? They're trapped inside the atom. If they have zero kinetic energy, they're free. If they have positive kinetic energy, they're free and moving. If they have negative kinetic energy, if they have negative energy, they're trapped in the energy well. Okay? All right, so tell me this. If I want to take this electron from here to the second excited state, or n equals 3, what photon is required?
A 7
Oh.
eV photon.
Why? Because it jumped from negative 13 to negative 6. The difference between the two is
7.
7. So that's E equals HF. That's a 7 eV photon, HF. You can figure out the frequency of it, and you can tell me whether it's going to be visible or not. That one probably not. I think visible is somewhere between around 1 to 3. It's like 1.5 to something or other. It's 1 to 3, somewhere in that range. Okay? Now look. If I want to take this electron all the way up to here, what photon is required? How much energy?
12.
A 12 eV photon. Now wait. If I take this electron all the way up there, oh, back up. What if I hit this thing with a 3 eV photon? I'm down here and I hit it with 3.
Nothing happens.
Nothing. It cannot take it, can it? Because it cannot exist here, right? It can only exist here, 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 and anywhere above here. If I hit this thing with 13 EVs, what will it do?
Go to 0.
It'll go to 0, it'll be ionized. What if I hit it with 15 EVs?
Fly off.
It'll fly off with how much energy?
15.
2 EVs. Could you figure out the de Broglie wavelength of that electron?
Oh.
Yes, you could.
Sign language.
Yeah. Now, what if I hit this thing with 12 and it jumps all the way up to here, and my electron's hanging out up here? Ooh, you can't see that. And my electron is hanging out up here. Is it stable up there? Will it stay there forever?
No.
No.
No. What'll happen?
It'll start losing.
It'll lose energy eventually and fall back, right? Because it'll fall back to less energy, right? And if there's an open place for it to go, it'll fall back there.
Right, so it doesn't fall back. And wait, hold on. Does it fall back? It can't fall back gradually because
It could. What are all the possibilities of what I could see, or the photons that it would emit, falling from here? It could fall and eject a 12 eV photon. Or, what else could it do?
5.
It could fall from here to here, and then from here to here, right?
Yes.
So it would eject a what?
7.
7 and a
6 packets.
5.
7?
6.
2 7s?
No. There's not a
No.
Failure there.
5.
Oh, that's a 5.
This really cannot add.
I cannot add. I was looking at the wrong one. All right. Or what else could it do?
5.
It could go from here to here,
5.
and then it could go from here to here, or it could go from here to here, and then to here, and then to here. So right here it would eject a
5.
5
2.
and a
2.
7,
Oh. Well, no.
or it could do a 5
5 2 5.
and a 2 and a
Cinco.
5. So, if it absorbs a 12 eV photon, you could get a 12, a 7, a 5, and a 2 EV photon back.
4.
Is there a 4?
No.
No. 12, 5, 7, 7, 5, 5, 5, 2. All right? You could get any of those back. Okay? What if I hit this thing with energy from from 3 to 6, 3 to 6 EVs of energy. Starts down here, hit it with 3 to 6. Where is that? Well, 3 would take me up to up to here, negative 10, and 6 would take me up to
The middle of the other one.
up here, negative 7. So what in that band could it accept?
Only that.
Only to there, right? So if I hit it with anything from 3 to 6 EVs, then it will end up in this range, but it will only accept this one, which is a 5 EV photon. That's the only one it can take. Does that make sense? So that's from chemistry. That's an absorption band, right? If you hit hydrogen with all range of energies of light, it will only absorb certain ones. Right? Okay.
So if you hit it with with 6 or whatever, would it go down to -7 and back to -8 and stay there, or would it just not do anything?
Okay. If I started here and I hit it with 6, remember they occur on a 1-to-1 basis, right? So if I hit it with 6 EVs, that would take it to here. It can't take it, so the 6 EVs will not be accepted.
Right, so it's not even going to go to anything.
It's not even, no, it's not going to do anything. None of that occurs because it can't take it. So it'll be scattered. Okay?
So it's hit with 6. It doesn't even get that 5. It
No.
just drops back.
It can't take it because it can't take part of a photon. It either takes the whole photon or nothing at all. Right? Does that make sense? Okay, that's going to show up on the test somewhere. All right? And then we got our very last thing in quantum, and then we go on to nuke.
We should have done it again.
All right. Our last thing is called
What is that?
Bum, bum,
antimatter.
Anti-
1929.
It does not exist.
A dude by the name of Dirac was working through what was called QED, quantum electrodynamics. So we had gone from classical physics, and within 30 years, we now had quantum electrodynamics. All right? And when he was working this out, coming up with this theory, working with the theory, he came up with something that popped out of the equation that looked like matter, but with the opposite sign. Okay. Scientists were telling him, most of his friends were telling him, well, look, just like you do when you're solving a quadratic, you got the positive root and you got the negative root, and usually it's the positive root you want, right? So you throw this one away. They were telling him, well, it's just a mathematical anomaly that there's no such thing as matter with the opposite sign. That doesn't exist. So just throw it away. And he went, no, I don't think so. I think I'm going to hang on to that idea. And he called it antimatter because it had the opposite sign. Turns out it's there. Okay? Antimatter is the same as matter except it has the opposite sign. And the peculiar thing about antimatter is that if you have a normal negative electron and you have a abnormal anti-electron, which is called a positron, and they touch, they will completely E equals mc squared annihilate and turn into total energy. So they will turn into a photon. So the mc squared of this one and the mc squared of this one will turn into a photon.
It's still alive.
No, it's not. And here's the crazy thing. That means if you have a photon of just the right energy, you can turn it into matter. You can create mass.
Yeah.
Exactly. It's still alive.
And it's basically just at the...
Because they told you to
Everything's
create
the same.
We created Georgia School.
Yeah, so the deal is, hang on, sit down.
Mass at 1 energy.
No,
is
sit down, sit down. So the deal is, sit down. No, you're not. You're standing sitting. All right, so here's the deal, is that we have to adjust our ideas of conservation of mass and conservation of energy. Now it's conservation of mass energy. So what we now did is we expanded the law of conservation of energy and mass to include each other. So now, like, this is perfectly acceptable. But what must also be true is you have to have conservation of mass energy, you have conservation of charge, So the charge before and after have to be the same. My photon, how much charge is that?
None.
0. How much charge does this have to begin with?
Total 0.
0, total 0. And we have conservation of momentum. So if these two things were flying at each other this way and this way,
Momentum is just a 2x.
yeah, then the x components here and here must add up to be the momentum h over lambda of my photon. So wait a minute. What if I have a positron and an electron? They're barely moving and they touch and they annihilate into photons. Can it create a single photon?
Yeah.
No, it must create at least 2, because the original momentum is 0, so therefore the final momentum must be 0, so therefore it has to at least turn into 2 that go in the opposite directions. Or it could turn into multiple that spray out from the center. There you go.